unmuted? So it's my pleasure to,
No, I've got too many things.
Right, that was my point.
Okay.
Go ahead.
oh, I was muted, sorry. So it's going to be a great session this morning with materials. We've got Ryan, a wonderful roundtable, and then James. So and what we're going to do is ask each person to cut 5 minutes off of their time so we can take a 15-minute break after Ryan's talk. So I'm going to time everything that way. And you guys are professionals, you can handle it. So Ryan, I've known for decades, long before I got to the Magnet Lab. He's been in the Magnet Lab about 10 years at Florida State University, and he's on his way to UC Santa Cruz. So we're gonna all, spreading around the planet. So take it, Ryan, great work.
Thank you, Laura. I actually don't remember when we met either. We were trying to figure that out the other night.
But we were collaborating long before we met. So,
Yeah, that's true. All right, well, first of all, it's a pleasure to be able to be here. I don't know how anyone would choose me to give a talk, but I appreciate it very much. And what I want to talk about today are some thoughts that I've been working on over the past several years. I've worked for a long time in strongly correlated F-electron materials. And I just want to tell you, what I've been thinking about with respect to how we can think about designing these types of materials. So the title of this talk is Strategies for Designing Quantum Materials. And maybe the subheader for this is Strategies for Designing Quantum Materials that even someone like me can understand. Okay, so that's where we're coming from. All of this has been done at the Mag Lab at Florida State University with support from funding agencies shown here in the state of Florida and the Mag Lab. All right, so something that we've talked about all week is this question of, well, what even is a quantum material? And in some sense, everything's a quantum material. We don't get to turn quantum mechanics off whenever we want, but that's also kind of a useless definition. So let me try to narrow it down a little bit further from my naive viewpoint. To me, a quantum material is one where the wave-like character of the electrons really takes over and just rules the behavior that we see. But that's not all, because there's other factors that are in play that we care a lot about. There's the spins, there's the structure, right? It's symmetry. Is it high symmetry, low symmetry, what have you? Orbital degrees of freedom, and many other things besides, right, that we care about. And we always think about these things as kind of building blocks or Legos or what have you. And so a second sort of important piece of this puzzle to think about is when we talk about quantum materials, we're really thinking about how these different degrees of freedom are combining to produce the collective phenomena that we care about, right? And what I think is exciting about this, and it's another aspect that I think is important just for bringing people into the field, is that each class of these quantum materials are really their own universe, for the electrons that live inside of them, right? And that's something we care about. It gives us basic science, but it also gives us opportunities to find phenomena that are really incredible. So that's, I think, the charge that we're sort of chasing down all the time. And we want to know how to do this more systematically. All right, so what about this idea of collective phenomena? Well, I think we were having a conversation the other night about going back to old problems. Even if I don't have anything to contribute on the Fermi liquid theory, I think it's still remarkable. It's something to reflect on. And that is that, we know about the electron as an individual particle. It has charge, spin, mass. It experiences the Coulomb interaction, which is really, really strong. And so you might think that if you took a large number of electrons and crammed them down into a solid, there's just absolutely no way that they would stay put. But we know that that's not what happens, right? We get metals and other things besides. And this is just this incredible example of how electronic phases are characterized by their collective behavior. We absolutely care about this. And this is really not the only example, right? There's many others besides. And they're the great triumphs of the 20th century, right? Like superconductors give us the ability to have medical MRIs. Semiconductors for communications, permanent magnets for so many applications, and many other examples besides. So this is, our entry into why we should be doing this. And I think we all hope that there's next generation quantum materials that will be just as impactful. So we can make long lists, and I'm sure everyone here has a different favorite sort of thing that they want to think about. What I've been focused on, and especially care about, are materials with strong electronic correlations. And we see things like the breakdown of the Fermi liquid. And we also see things like unconventional superconductors and really unusual magnets and so on and so forth. So that's where I'm going to focus today, is in materials with strong electronic correlations. All right, so let's see what we can do there. So I've said, collective states matter. We have all these different building blocks. But there's one other thing that I think as a community, we've not ever really been able to get away from. And that's the fact that serendipity matters, right? And a really wonderful example that we've heard about this week, I think a lot of people have thought about, is uranium tellurium-2. And just to quickly go through the history of this is a nice figure of resistivity versus temperature that I stole out of this paper that I think captures the history pretty nicely. And it goes like this, back in the 2000s, I think Onuki, and maybe, I don't know the whole history, but Onuki reported on this material when it was grown out of a tellurium flux. And it produced a sample that had a resistivity curve that looks like this. And we might say that this isn't a very high quality specimen. I don't really know. This is a complicated material. But in any case, it has a large residual resistivity. And it doesn't superconduct. So these guys did what anyone would do. They reported this, and they moved on. How could you possibly know that you should make a lower residual resistivity sample of this particular thing? I don't know how you could. In any case, some years later, JP and Nick Butch and Sheng Ran, I've asked specifically, they weren't trying to make this particular material, but they were using iodine vapor transport to grow something else. This came out, and not only did it come out, but they had the good idea to measure it to low temperatures, and they had an ease of being able to do that, right? The cost of entry for their group was not so high, so they just measured it. And look what happened. Now we have this incredible burst of interest, developing this material, getting higher quality samples, finding this unbelievable and strange high field phase diagram, and much more besides. All right, so serendipity matters. We really haven't made it to a point where we can get past this.
Sounds like having a dilution fridge matters.
Sounds like having a dilution fridge matters. And actually, let me expand that just a little bit further to be philosophical about this. Low cost of entry matters, right? You need to be in a situation where doing things is not incredibly difficult. I know that sounds easy to say, but that's what we want. We need experiments that seem hard to actually be easy, so people will do them. Okay, so serendipity matters. And just to give a little bit more, to push this a little bit further, here's our famous plot of TC versus time for all these different families of superconductors. And this story, plays out again and again. Even the first superconductor, was a serendipitous discovery. And by the way, it related to a new technology, the ability to liquefy gases, right? No one could have done this without first developing how to liquefy gases. So that ease of entry, not that it was easy, but it created a new ease of entry, and it kicked off, more than 100 years of research. Well, that was followed by a period of refinement, maybe best exemplified by the work of Bernd Matthias, but many others as well. Developing these types of so-called conventional superconductors. But this story plays out again with strongly correlated electron superconductors, F electron superconductors, discovery by Steglich, and then refinement that is ongoing now. C60 superconductors, although I think in talking with Art, the serendipity part maybe I'm pushing it too hard, but we can talk about that some other time. Cuprates, we see this, serendipity followed by refinement, and iron-based superconductors. So this really is our story, and it's very hard to get away from this. But we want to, and we've been trying to. And one of the things that has become very clear is that when we think about these types of materials, the collective states are really often found in close vicinity to each other in the phase space. So we have really rich phase diagrams. And these phase diagrams start to look universal, okay? This is just stolen from this nice paper here for cuprates and iron-based superconductors, and I'll just say what we all know, and that is that the parent compound for the cuprate is a mod insulator with a magnetic ground state. That doesn't seem like a great place to go looking for superconductivity, but if you tune it the right way, magnetism collapses, it becomes more metallic, although it's a strange metal, and then superconductivity. Similar story here, although the starting condition is different. And by now, there's really, probably dozens of phase diagrams that look like this for many different families of materials with many different parent compound behaviors. So it starts to feel like some sort of design principle. But I want to throw cold water on that too, because there are plenty of examples where you can start with some ordered ground state and tune it in some way and not get this. And we saw that this week in Joe's talk, right? He's telling us about these flat band D systems. Seems like the right condition to tune it and get here, but it doesn't work. We don't know why it doesn't work. Maybe it can work, but it's not working yet. Okay, so this is very appealing, but it's also not sufficiently good to let us know what to do. Okay, so that's fine. And well, there's even more to say because if you broaden your scope, there's just a tremendous variety of different types of phase diagrams that are all very interesting on their own. And in some sense, I would say that many of the talks that we've been hearing about this week are exactly this. Right? Maybe I've stretched it a little bit for some of these, but I think in many cases, we're just looking in the phase space and trying to find what sorts of trends are existing between these different collective states. Okay, so exciting, interesting, but also somewhat open-ended, right? And that's the criticism that the funding agencies always tell me. Okay, so I want to put this in a different way. We actually have a really serious challenge in developing new materials, and it's just a numbers game, right? So there's something like 100 elements. If we just look at the number of possible combinations, it grows incredibly fast, but actually, this isn't even good enough because we know that we want to tune materials. We have to tune materials to get to the places we want to go. So the phase space maybe is effectively infinite, at least on the lifetime of a human being. It's probably not truly infinite, but it's very, very large. We can't have a hope of getting through all of this following a brute force approach. Okay, so in this talk, that's my preamble. That's where I'm coming from. And in this talk, I want to think about harnessing serendipity. Are there any new ideas under the sun? So what I'm going to talk about is some thoughts that I've been working on, thinking about how to connect the electronic, magnetic, and structural instabilities that seem so appealing for finding interesting behaviors to chemical structural phase diagrams. And I'm going to do something really rudimentary, but I think that it's a nice starting point. If I have time, and I know I'm supposed to take 5 minutes less than...
No, don't take that with the pictures.
I'm just joking. But then I'm going to say something else. I think it's very nice to think about going into unusual regions of the chemical structural phase space using different methods. And there's plenty of different ways to do this, but one that we've been working on is synthesis under applied magnetic fields. So 2 different ways of trying to deal with this big problem. Okay, so we're at UC Santa Barbara. We want to think about the quantum materials foundry, and here it is. This is the quantum materials foundry. So we have the periodic table, and if we want to think about how we're going to deal with this, we have to wear 2 hats, at least. And the first hat is the physics hat. Right? We want to think about these different parts of the periodic table, like Paul Canfield says, like we're chefs. There's different flavors that we can get out of different regions of the periodic table. We're not going to go to alkali metals and alkaline earths to find strong local moment magnetism. We want to be aware of these different ingredients, think about how to put them together in intelligent ways, but we also have to put on a chemistry hat or a material science hat. And, there's other challenges here. We can't just arbitrarily make whatever we want using whatever crystal growth method we want. On the one hand, alkali metals, alkaline earths, they're pretty nice because they're easy to melt, but they're air sensitive. That's some problem. Or transition metals, not so air sensitive, but much harder to melt. And so having this big toolbox of knowing, about the physics phase diagrams and the chemistry phase diagrams is something we have to do. And so that's something to think about too. Okay, so we want to make targeted studies. And there's this overarching idea of the materials genome strategic plan. And it involves all sorts of things that I myself don't know how to do. Computational methods, ab initio calculations, machine learning, deep learning, so on and so forth, although this does seem to be getting more and more accessible. So what we decided to do was to sort of look backwards into the literature and try to take advantage of the materials data that already exists. And I know lots of people have done this in lots of different ways. A different way of making this statement, and this is something that I really think is important. You know, it's very normal for us to try to study exciting materials. You know, we all want to study uranium, thorium too, because it's so strange and it's going to produce publications. But I really think that a full understanding requires knowing why the boring ones are boring too, right? So a full understanding of these types of materials would take, you know, having a, I don't know what the right word is, a holistic understanding of why the boring ones are boring and why the interesting ones are interesting. So going back and trying to find all the examples that no one cared about actually has some value. Okay, so that's what we decided to do. And that's it's an intractable problem, at least for me. So what we decided to do was to focus on the thorium chromium 2 silicon 2 type structure. It's a very large family of materials, and it's also a very simple family of materials, at least structurally. And that structure is shown here. Probably people are familiar with it, but just in case you're not, let me just say that you have these A ions on the square nets in the body center. Then you have T and X on these corrugated layers. The A's can be alkali metals and alkaline earths. The T's can be transition metals, right? And the X's can be these P block elements. And there's all sorts of flexibility in here that we can play with. So that's at least my type of chemistry dream. You know, we can do all sorts of things. There's over 1,000 known combinations and all sorts of different collective states like magnetism, charge order, superconductivity. But actually, it turned out that as we started to work on this, this was even too large for me to deal with. So we decided to narrow it down just to the F electron examples. So that's where we're gonna go now. And anyways, we know that these are deep reservoir for unusual phenomena. So let's go there and see what we can learn. This was done actually in collaboration with Julia Chan at Baylor University and my former graduate student, Yu Lai. And what we wanted to do was to take a purely phenomenological approach and sort of pretend like we're astrophysicists or something. We decided to take all of these examples, write down their sort of rudimentary properties, and just sort of stare out into nature and see what we see. Is there any sort of trend? So here's all of the cerium-based 122 compounds with this structure. We did this for other lanthanides as well. I'll show you that in a minute. And what you see is, you know, there's all sorts of behaviors. Some of them are polyparamagnets. Some of them are sort of regular antiferromagnets. Some of them are condo lattices. And then, yeah, there's some of these really special examples like cerium copper 2 silicon 2, which is one of the first unconventional superconductors. And at first glance, you know, we don't really notice a pattern, just that there's a lot of variety. But luckily, you know, there's been decades of interest in these. People have poured all sorts of effort into it. And so it's possible to start to develop some sort of insight. And using that, we decided to try to organize these in terms of parameters that might matter. And also we wanted to organize them in terms of parameters that are really easy to access, right? You don't want to have to think too deeply about the paper from 1978, right? And you know, we wanted something that in principle, maybe a computer could even do the work for us. We haven't gotten to that point yet. All right, so we organized them in terms of their unit cell volume and in terms of their D shell filling. And in some sense, this is a little bit like a periodic table for these compounds. And what did we find? Well, sure enough, it actually organizes them very cleanly. And people who are experts in this field probably aren't too surprised. But let me walk through this. So in one region of this phase diagram, up here, we find that if the unit cell volume is large and the D shell is more full, you get more of a magnetic ground state. If it's compressed and less full, you wind up with a non-magnetic ground state. And right at the interface is where you find these interesting examples that show superconductivity and so on. All right, so this is nice. It looks like it works well, but we want to start asking some questions. Why does it work? And does it work well for any other groups of materials? Or is this some sort of accident? Okay, so people have worked on cerium compounds, extensively. And you can see that this really does make sense from what is known about them. And the first thing we want to know is that cerium can take two valences, 3+ and 4+. If it's 3+, it has one F electron in the F shell, and the SL and J values are shown here, gives us magnetism. If it's 4+, there's no F electrons, we wind up non-magnetic. So it's immediately clear why there would be some that are magnetic and some that are non-magnetic. Okay, but we can go further. There's this well-discussed and established Kondo lattice phase diagram where there's all sorts of interactions, but an extremely simplified perspective on it is that there's two that really matter a lot, and those are the RKKY interaction and the Kondo lattice interaction, right? So RKKY is this sinusoidally modulated polarization of the conduction electrons. And then you have your F elements, and depending on where you put them, you can have an antiferromagnetic exchange, a ferromagnetic exchange, or maybe even no exchange at all. In any case, this is one that favors a magnetically ordered ground state, and that's illustrated over here. On the other hand, the Kondo lattice, there's so much to say about it, I won't try to say much of it at all, except that what happens here is that the conduction electrons like to screen away this local moment. And it will tend to give us a non-magnetic ground state. And if you tune these the right way, they're in competition with each other. You can give a quantum critical point. Sometimes there's superconductivity, and then the emergence of this weakly magnetic Fermi liquid. And so, this isn't new. Everyone, I suppose, knows about this. But the useful new thing that comes out of building the map this way is that now in the chemical structural phase space, you can identify, where are you going to get this? Where are you going to get this? Where are you going to get this? So that can constrain the way that you make a search. Okay, well, just a little bit more about this, putting the chemistry hat back on and not thinking too deeply. What are we doing when we change, along the d electron axis? Well, maybe what we're mainly doing is tuning the density of states. What are we doing on the p block? Well, here, we can do a little bit of shell filling if we go this way, or we can change the unit cell volume going this way. And that all maps pretty nicely back onto this, right? So now we can claim maybe that we have some sort of understanding where RKKY wins when the unit cell volume is large and the D shell is more filled. Kondo tends to win, or even 4+, when the unit cell volume is small and the D shell is less filled. And now, we know right where we ought to go if we want to find quantum critical behavior and hopefully superconductivity, and maybe other things besides. All right, so this is pretty good. At least I feel pretty good about it. But the next question would be, does this work for any other systems of F elements or structures or what have you? Right, so I want to remind you that amongst the F elements...
Sorry,
yes.
Ryan, for the plot that you have before, the color scale,
Yes.
what does it represent and how did you come up with those contours?
It's somewhat
I know it
arbitrary.
represents magnetism.
Well, it's
but
not entirely
it's
arbitrary.
measuring, actually.
It's not entirely arbitrary, but it's not quantitative. So what you will see, if you look carefully at these types of guys, is that the hybridization is quite weak, and the magnetism is extremely, it's like really local moment magnetism, right? And the magnetism is weakening as you make your way into this crossover region.
As measured by...
As measured by, you know how if you were to measure the strength of the Kondo hybridization and how it's suppressing the moment itself as you approach that crossover region, it would be something like that.
So you
Or
look at
maybe
the
look at the
susceptibility,
entropy.
for example.
The susceptibility or the magnetic entropy, those sorts of things.
And the tilt,
Yes,
that's because you've got many more d electrons on the left-hand side, is that the reason?
I'm going to show you something interesting in a
Okay.
second. I believe the tilt has to do with the fact that the condo interaction is present. I want to show you something interesting
I'm
because
just kind of confused how you got the tilt though, like that's
Yeah.
the issue that I'm having, is that you've
Yeah.
drawn those contours, so
Yeah.
that you've already, but it seems like you've already known where to draw the contours, because there's no quantity that it's measuring, so how do you know?
Yes, so you're worried about whether or not this should just be horizontal, for example.
I just,
You want to know?
it just seems like you already knew the answer before you drew those
And in a
contours.
sense, in this family you do, I think. In this family you do, because it's been studied so heavily. So you can go into studies, people have examined the effect of pressure, chemical substitution, and so on, in a lot of detail in this family. So this one, I think that you, in a sense, you do know the answer before you start. But it's a good starting point for trying to build out into other families of materials and figure out what these trends would be. Okay, let me go to the next thing, and I'll show you what happens. Okay, so we wanted to ask a similar question in other F elements that have unstable valences. And a lot of these guys, they don't. So these are kind of ruled out in terms of thinking in this way. But all of these other guys, and down in the actinides, do have multiple valence states available. So in principle, this sort of behavior might show up as well. Okay, so does it work for other examples? Well, here's what we've done so far. In uranium cases, there's a clear separation between non-magnetic and magnetic examples. Europium, ytterbium. Here you'll notice that the magnetic and non-magnetic regions are flipped. That's because of the whole electron difference between ytterbium and cerium. It works reasonably well too for these less well-studied pnictide examples. But I think this is relevant to both of your questions. You see the trends are different, right? So for uranium, I find this very interesting because, we generally think that uranium is in some ways analogous to cerium with the condo lattice and so on. So we might think that there would be, well, at least not a purely vertical order, but there is. Right? So in this case, there have been works pressurizing these types of things, hoping to get them into a more quantum critical regime. My statement is that whether or not we understand the physics of why it's like this, it's totally pointless. Pressurizing these is not going to take you into this crossover region. I also think it's noteworthy that uranium ruthenium-2 silicon-2, which is the only superconductor in the family, is close to the crossover region. So, this, again, your question about how...
They're all close to the crossover region.
Well, these guys are. These guys are not.
All the ones next to uranium, ruthenium-2
I
silicon.
totally agree. I completely agree. And to me, that motivates further efforts to take any of these guys and get them to hop across this.
But so, that was arbitrary, right? You could have moved them anywhere you like into the blue region.
Which ones?
I mean, just following up on Jim's thing, we love this stuff, but if we want to be critical, we don't really know how close to the crossover
I agree.
they are.
I agree. And the other thing we don't really know, and this is part of your criticism too, this is very simplistic. It's incredibly simplistic, right? What about how these things might dance back and forth, in this way? It's clearly a very crude model.
Well, the other comment would be that in uranium, this color, if you take the darkness of the colors seriously, it should be much deeper, right? I mean, the magnetic uraniums are hundreds of Kelvin, whereas the cerium ones differ by tens of Kelvin.
That's a good point too.
That's a quite different
Yeah.
system.
Yeah. So,
But do you have an idea of why it works for iron, ruthenium and osmium, that one column, and you don't get itinerant behavior for any of the others?
no, I don't.
I think you'd have thought it would taper off, not suddenly die, right?
You would think. I don't have a good answer for that, but I think that the value of looking at it this way is that it lets us ask those questions in a systematic way.
Well, clearly it has to do with the hybridization of the F electrons. It's the only actinide in the system, so it has a completely different electronegativity compared to the others.
So can I just ask, maybe I missed it, but how are you defining the white region? Because for some of these families, it's like really big, and then for other ones, it's like a tiny little.
It's a very good question. Yeah, it's a very good question. So okay, so the place where it is the biggest is here in the Ytterbium family. And in this case, what you find is that actually there's a very large span of them that really just show condylattice behavior without an ordered state. So in that case, I would define this white crossover region as any of these examples that, you know, don't show magnetic ordering. They show some hints of Curie-Weiss behavior. And then I just have to spread it out over them because within the crudeness of this model, I don't really know how to distinguish, you know, between this type of behavior and this type of behavior. But I think if you really wanted to know, you know, about this, how sharp are these regions? If you really wanted to know, one of the next steps would be to carry out some chemical substitution studies that are spanning this. And I think it tells you, you know, if you, I don't know how to find a new hidden order compound. I'm not claiming that. But if I wanted to take a wild guess, I would say that I need to work somewhere in this region, and going anywhere else doesn't make any sense at all.
Ryan, can I ask, what do you think is the physical parameter along the x-axis?
So yeah,
Because you could say.
I've simplified it in my mind to band filling, which tunes hybridization strength. And the reason that I've done that, and it's not included here, but I have some experimental results that show this, is that in many of these systems, you can do chemical substitution on the transition metal site. It'll produce a phase diagram. You can also do chemical substitution on the p-block site, for example, going from silicon to phosphorus, and it produces almost exactly the same phase diagram. So somehow band filling is kind of a universal parameter that controls hybridization strength in these things.
But if it is just like band filling, shouldn't it be always a vertical line to white line? Why they become like horizontal for some cases, tilted for some cases?
It's a great question. I don't have the answer to that yet. I want to point out one other thing that may stimulate some other conversation. I think in the europium case, it's pretty hard to make any sort of argument that it's, you know, going like this. It seems to be pretty horizontal. And it's just interesting to note that compounds like europium, palladium-2, silicon-2, sitting right here, this is a compound that undergoes a valence structural transition as a function of temperature. As it cools, it undergoes a valence transition. And I think it makes a lot of sense that it's sitting right next to this. So if you want to find behavior like that, you know, go into this type of region. So at the very least, this provides us with a map for where we would go to find competing states.
I don't want to delay you even more.
No, it's totally fine.
There's another parameter which we thought about some time ago in this structure, which is the dimerization of the green atoms you have.
And it's especially important in these guys.
And yeah, there is a line in the periodic table that kind of crosses that regime.
So I'm going to talk about something like that in just a minute, because this isn't the only possible way to build maps. Okay.
Yeah, okay.
Okay, so this is an idea. I think it's you know, able to stimulate some conversation. And I think that, you know, even if we don't understand everything about what's going on here, it tells us about how to focus ourselves in the chemical structural phase space and be able to ask the right questions. Okay, all right, don't need that now. Okay, so here's just a very quick summary of some of the systems that we have studied. More to come, but one that I already touched on it, but we did focus on uranium, ruthenium-2, silicon-2, doped with phosphorus. Found this sort of phase diagram where hidden order is suppressed, superconductivity is destroyed, eventually antiferromagnetism emerges. People who are familiar with this material will probably remember that this is very similar to what happens when you replace ruthenium with cobalt, iridium, or rhodium. So that's telling us something about how it doesn't really matter how you traverse from left to right. It's going to do something similar. Okay, so I wanted to make the remark that these thorium, chromium 2, silicon 2 materials are interesting, but they've been heavily studied. And we'd like to push this into other families of materials. Maybe the best way to get started on that is to look into some of the closely related structural variants. We've started doing work on this. These families are much less well populated. So it's a little bit like going out, in a boat where you don't know the contours of the land around you, but you know some pieces of it. And so I think it helps you to navigate to know where you want to go. By the way, cerium, rhodium 2, arsenic 2 has been attracting some interest recently, and I think it is actually very close to that crossover region. Okay, anyways, there's other things like homologous series. This is from Julia Chan, where you can take these sorts of elements and build them up into structures. Of course, this creates a unbelievable problem in terms of how many different variations you might want to study. And again, here we've been trying to use this type of thinking to constrain ourselves back into, what regions might show really unusual emergent states. So this is something we're trying to do. And then of course, it would be wonderful to expand this into some computer-driven methods, but we haven't made it there yet. Okay. Now, so this whole picture does kind of depend on thinking about instabilities and valence instabilities and competing interactions and so on. And I do want to say that, like JP was alluding to, there's many other types of instabilities that we could start thinking about. And one that I like, this is also from Julia, is to think about something called a tolerance factor. So in many families of materials, you can make some structure up to a point, depending on the size of the atoms that are in there or the size of the cluster or what have you. In the 1,2,2s, this dimerization, there's all sorts of things like this. Well, in some of them, there's something called a tolerance factor, where if you exceed some certain parameters, don't ask me to explain this right now, because I don't remember, but if you exceed some conditions of size, the material will snap over into a different variant of that structure. Okay, and that happens for these Ramika phases. She's been looking into that. What I think is especially interesting is if you could put into...
When you say size, you mean like coordination of the lightest element or something? Or like
Yeah, or,
how do you define
here's
size?
an example. Here's an example.
Nearest neighbors, is that what you mean? Or?
Well, let me just give a very simple example. In the 1,2,2s, there's uranium, ruthenium 2, silicon 2. If you try to make uranium, ruthenium 2, germanium 2, it will not form in the same structure. And it snaps over into a different thing altogether. That's probably like the simplest possible example where just the germanium is bigger than the silicon. I'm sure there are more complicated variants of how to make a statement like that. So what I think is interesting here, and trying to build off of those maps a little bit, is to think about what would happen if we put an element in here, like ytterbium, that has different valences available to it, and that are right on the verge of crossing over in this tolerance factor type of thinking. And then just one further statement that I was thinking about earlier this week when we were talking about uranium tellurium 2. Right? Remember, it has a very unusual structure by comparison to the other dichalcogenides. I think that's yet another sort of sign of how you would go about searching for really interesting materials. Take a computer, get it to look at common structure types, and look for the examples that are just different. I think you'll almost certainly find something unusual there. Okay, so these are my thoughts about how to focus searches. So how much longer should I go for, Laura?
Go ahead.
I've got time, okay. Okay, so now I'm going to completely change gears, and I want to say something different that has much more to do with synthesis. Okay, so when we go out and we try to make materials, I think many of us are using more or less similar growth methods. And this maybe is having a tendency to push us into similar results as well. And so we have these different types of methods, like solution growths, vapor phase, thin film. This is pretty new, but very exciting, 2D layers and stacking, melt growths, and so on and so forth. But it may have the disadvantage of sort of driving us back into similar parts of the chemical structural phase space. And we want to get outside of that. So I think it's interesting to think about how we would actually do that. And at the Mag Lab, one effort that's been underway is to think about materials growth under extreme conditions, and in particular, materials growth under applied magnetic fields. Okay, this is the group of people who have mainly been working on this. And our motivation is just shown here. If we think about the Gibbs free energy, we're familiar with all these terms. But what happens if we throw on an HDB term? Will the ground state of the system depend on applied field? And there's an argument that comes up immediately from most people, and that is, how can it possibly matter? If a Tesla is a Kelvin, how can this energy scale possibly matter? Okay, it's too small. We do all our growths at above 1,000 degrees C. This is too small to matter. Well, I want to tell you that actually we think that it does, and there's several reasons why it potentially could matter. And so to begin with, it's already very well established, to the point where it's even used in steel industry, that magnetic fields control the microstructures of alloys. So in that sense, this is already well established, but for our sorts of work, I think it's fair to expect that an applied field would also have an impact on precipitate formation. And I also just want to say that in these strongly correlated electron systems, we know that you grow it a little bit different way, you look at it the wrong way, and its behavior changes, right? This means that there's very fine tuning that wouldn't necessarily require large energy scales. So for example, for uranium tellurium-2, I think there's some interesting questions to be asked here. But that's not all. This concept that a Tesla is a Kelvin may not really be spot on all the time, especially if the G factor is larger. So for lanthanides, for example, in a field of 18 Tesla, it starts to become more like 60 Kelvin. If you can pull your growth temperatures down, maybe using low melting temperature eutectics, then you start to get into a regime where, remember your binary phase diagram, that's temperature and chemical composition, can start to have a new axis coming off of it. I think there's lots of opportunities there. Of course, growth in fields will do things like change convection, result in preferred growth directions. And then one that I think is really pretty interesting is that magnetic fields might be able to produce metastable phases. So just think about how, I think we were hearing about in chalcogenides, and I'm going to give an example in a second. There are different structural phases that are pretty finely spaced with respect to each other in energy. So you don't need a large field to necessarily have a big impact on level form. And indeed, this sort of work has been happening. This is from a group in China where they've been doing magnetohydrothermal synthesis of these dichalcogenides. And sure enough, in a field of 0 Tesla, you get one structure. A field of 10 Tesla fully converts to the other structure. So this is totally wide open. It's almost like you can read all of the literature in this field. So much work to be done here, and I think the message is stay tuned.
When you say G factor is 5,
Yeah.
that's referring to an effective spin of a half. In other words, if because the Landé G factors are usually below 2, right?
Mm-hmm.
But so I think. But
In lanthanides, they are large.
is that right?
Yeah, semi-magnetic, semi-conductor.
The Landé G factor.
Mm-hmm. Mm-hmm. Yep. Okay. All right. So
You have a feeling for what the mechanism is? I mean, you polarize the spins at high temperatures. That's not going to change is that going to change the shape of the ions or their interactions with the other? It must be changing the interactions between the ions, but
yeah.
how is it doing that?
So let me try to approach this from a different direction. I think that when we do crystal growth, it's a little bit of black magic. We don't really know what's happening, right? And there are some new capabilities to do crystal growth and do in situ monitoring, right? You can do a neutron scattering experiment and watch what phases form and when they form and all this sort of thing. You know, when I take my very naive view of crystal growth, I like in a molten flux, I kind of think that I put stuff in there, I heat it up, it gets all uniform, I cool it back down and things form. But I think that must not be true, that there's different stages of, you know, and maybe dimers form, I don't know what. And so I think that many of these things are probably finely tuned.
Yeah, and intermediate structures may be field sensitive.
In fact, I know that there are intermediate structures that form because we did a recent study with Susan LeTurner, who did this for some ternary gallium thing. But we just know nothing about that. So it's important to figure that out.
Maps are like these equilibrium phase diagrams, but the process is an intrinsically non-equilibrium process of forming materials.
Precisely. Yeah, we don't know the answer to that. We need to know the answer to that.
Just a quick question. So when you're doing synthesis, for example, under high pressure, usually it's the case that after a few days or weeks, it relaxes back to the zero pressure structure. Is that the case here? Does that
In this particular case, no, it stays. This one stays.
Sometimes.
Yeah.
Sometimes, yeah.
So they were excited about this because this one stays.
Okay.
Yeah. Yeah, that's a good question.
But do they know what is happening, why mainly field papers want to?
No.
Not even hand waving?
Hand waving.
I have another question. In the melt, is there a orbital motion that's caused by just from a diamagnetic effect from the applied magnetic field?
I don't know. It sounds.
Because if there is, you can imagine there'd be different interface effects, so the nucleation points would
Oh
kind of
man,
change.
and let me tell you one, I'm really getting off topic. But let me tell you one other thing. We have even had the experience, no magnetic fields, no nothing. We've even had the experience where we change the crucible from being a 5 ml crucible down to a long, thin thing, and a completely different phase
Yeah,
forms.
the nucleation is really critical,
Yeah, it's like, okay.
So these are all static fields, but what about dynamic fields?
Yes.
That would give orbital.
Yes, and gradient fields as well
Gradient.
are another direction. This is really, I think it's really exciting. And so I've already been able to make my sales pitch, which is fantastic.
So, yeah, we could have discussed this yesterday morning, you know, how to stabilize metastable phase. This is a wonderful way. But I want to add two things. One is you're probably familiar with Geng Chao.
Yeah.
Has been doing this, who used to be also, you know.
That's right.
Tallahassee, and you know, flux growth and then small magnetic field and somehow that's all the magic. Oxide somehow near temperature changes with the different, you know, magnetic field. Second thing is, so in chiral systems, my understanding is James is going to discuss some chiral systems, but the chiral system is important to control left chiral domain and right chiral domain.
That's right.
And
Yes.
magnetic field somehow magically works.
Yes.
And nobody understands. So it's some kind of a nucleation process. In the very beginning, some magic happens, and then bang, it continues. Something like that. We got to understand better.
Yeah, we don't understand it. And actually, if I want to take that one step further, the pharmaceutical industry cares a lot about chiral structures.
All the chemistry.
Yeah.
Chemistry is based on chirality.
So that's not condensed matter physics, but there's a connection there now.
Yeah.
So, okay. Okay, so we're really just at the very beginning. I only have a little bit of time left, but I just want to share with you a result from Mark Meisel at UF and James Hamlin. And the rest of us have been involved in this, but this is really their work. So what we wanted to do, or what they wanted to do, was to see about growing something relatively simple in a applied field. And a good example here is shown in the cobalt-sulfur binary phase diagram, where you can see that if you combine them in the right ratio, the melting temperature comes down pretty low. And what's more, it drops below the Curie temperature. So it lets you ask some sort of weird question, which is like, what will happen if you do a crystal growth below the ordering temperature of the thing you're growing? You didn't know the answer to that, but as we tried it. The heating schedule is shown here. It's nothing too special. And the result of that experiment is shown here. So what you see is that when you grow these crystals in zero field, they turn out as these sort of nice cubic looking sorts of things. And as you turn on the field, they elongate and eventually wind up as these needle-like structures. So at the very least, it's impacting the crystal morphology. Probably the thing we care a lot more about is, does it change the magnetic properties at all?
What is magnetic field orientation? Is this way?
Yes, I think that's, I don't know.
You don't know?
I don't know.
It's a random process.
He's probably told me that, but I don't know. You're asking especially here.
Yeah.
Did it grow along the field or perpendicular?
Yes. You don't know.
I don't know. He's probably told me and I don't remember. But, okay, the punchline for the magnetic properties is that they're very similar. They really don't change very much.
Oh,
Okay, but let's keep in mind that this is actually a relatively simple sort of system. I think it's going to be interesting to do this sort of thing on our much more finely tuned materials. Who knows what this would do in a material like uranium tellurium-2? I don't know. But it gives us, a thread to start pulling on. It clearly does something. There's some other results that I am not allowed to talk about today that are exciting too. So stay tuned. Maybe in a year there will be more. Okay, and here's my advertisement, because this isn't just for me. It's not just for Mark or James. It's for everyone. It's part of the user facility at UF. It's part of the Mag Lab, where they've built up a nice 9 Tesla superconducting magnet that you can do flux growths in that'll reach 1100 degrees C. I'm sure that if you have an idea and you want to send them samples, they'll be glad to work. And then in Tallahassee, Kaya Wei has been building up a 5 Tesla wide bore superconducting magnet that's going to have a similar type of furnace in it. So I think real experimental progress can happen now.
you still don't have a floating zone type.
No floating
Not
zone,
yet.
but
I think you got to, they got to.
Yeah,
You got
they-
to. No,
they-
Laura,
yeah.
you are the boss there.
yeah, and well,
You
and
got
you
to
can
install.
Oh,
imagine.
yeah, I'm in charge of everything. No, but
Yeah.
you were giving a talk and someone brought up, what about you sintering some materials?
Yep.
in this? And there's, I hadn't thought about that, and this is a first step, is really a lot. So, float zone, let's do some of these first steps first, and, there's results, so.
Good.
Yeah.
I think that would be a good idea. We made what we used to call pseudo single crystals of the cuprates by aligning them in a field, the particles, because they were
That's right.
single crystals, and then embedding them in epoxy.
Yeah.
And then we could measure the easy axis and do all those things. But if you eliminate the epoxy and then you could sinter them, which we couldn't do,
Yeah.
then you could get something more closely resembling a real single crystal.
What's the possibility of doing in situ diffraction?
You'd have to do some work to give, well, what about in the split coil?
Yeah, split coil.
I mean, maybe,
Is there enough room?
I don't know.
I
don't know the
bore
answer to
size.
that.
That's Jan, yeah.
It's
I
not
don't think it's a
big,
very big bore size.
but a smart person.
Well, the X-ray
might
doesn't
be
have to
able
go into the thought, like, it's just the rays, you just need to get them in and out.
No, but if you're talking about as a function of temperature, like a lot of people do in situ X-ray diffraction while they're growing,
Right.
doing that in the field. We'd have to look and see,
It would require some engineering.
yeah,
I-
and, maybe a small sample with,
And maybe,
but
Well-
how would,
I don't know. I think we'd have to think carefully about how to do it.
Yeah, there was some discussion in, synchrotron facility, how you install something like this.
we've been trying that for
Yeah,
years.
it's
And
tough.
we might
Yeah.
get something, we're actually working on something with chess right now.
Yeah.
But we've been trying to get a magnet and that's politics, so go ahead.
Yeah. It's a great idea. I like that.
So this might help get
Yeah.
that,
Well, it looks like I've taken almost exactly the right amount of time. So I just want to say something a little philosophical now. I think that the search for quantum materials with novel states is really exciting and unsolved. I think, this meeting is evidence of that. But I also think that, even if these maps that I presented are very crude, they maybe can help us to constrain the way that we make searches. The phase space is way too big. We have to cut it down in some way. This is a type of work where physics, chemistry, material science, and data and all these different things have to come together. There was that nice graphic, I forget who showed it, of the wave functions adding together. That's what a quantum scientist is, I think. I do think it's a great training ground for the next generation of scientists because there's so many different nodes where they can connect, and that's an inspiring thing. And then, you know, anyone that's ever grown crystals knows this. Crystal growth inspires awe. When you take samples out of the furnace, it's like Christmas morning because who knows what you did? It's wonderful, and it's a great motivator for the next generation. So this is our fuel for discovery, and I just think it's wonderful.
What about all those? I was going to make a joke about lumps of coal, but it doesn't matter.
Do you have more questions? Yes?
What do you think are the kind of prospects for being able to visualize what's going on inside of a flux growth?
Oh, yeah. So what I understand about that, the only good way that I know to do it right now is with this neutron scattering capability. And the limitation there is whether or not you can get the neutrons in and out. So my understanding is that when Susan was doing that, she was intentionally doing gallium and aluminum fluxes so that it would be possible to do that type of measurement. Of course, we all want to use lots of other things. I think it gets a lot harder really fast.
But that's diffraction, right?
Yeah, that was diffraction.
I was thinking just seeing.
Oh, just seeing.
CT scan, has
Yeah.
anyone been trying to do something like that?
I love it. I mean, I don't know of anyone that does that.
Well, you know, so that's where the floating zone technique can be very
Yeah.
useful. Floating
Yeah.
zone, you can do anything.
Yeah.
Floating zone, if you do that, maybe field and floating zone, and you can do a synchrotron X-ray, you can do neutron,
And you're-
it's open, right? It's not closed.
Yeah. I hear a proposal.
Very nice.
I mean, I've been trying to convince Greg in the last 15 years, so, you know.
Well, let's talk about it, yeah.
Yeah.
Floating zone, you know, this laser,
It's a
these
video.
days really laser floating zone, it does really magic. You don't need much space. Use a small gap, and laser goes in and heat up, and then it does this.
That's wonderful.
Okay, let's talk about this in the next 15 minutes. We'll come back at 20 minutes to whatever time zone you're in. Okay. Thank you, Ryan.